Let us start by again reminding ourselves what exactly solving a problem in linear elasticity, especially linear isotropic elasticity, means. So we start here with a body which is deformable and is undergoing small deformations. The body can be subjected to firstly a body force field, which is a vector field of position. So we call it B, a vector field of position x, and then it can be subjected to surface tractions, which we will call t bar, and which can also be uh, functions of position. It's also a vector field. The body can be constrained in different ways. Okay, the body can be constrained in different ways, and the volume that the body occupies is called v. The boundary of the body is denoted by delta v. That is the kind of notation that we use. Now, the part of the boundary on which tractions are applied, and remember these tractions can be zero tractions as well, is called delta vt. So this is the part on which tractions are applied, and the part on which displacements are applied, the part of the boundary on displacements are applied, is called delta vu. Okay. Now let us take a point, arbitrary point x, with a with respect to a fixed coordinate system. Let us take a point x, and at each x in v, so for uh, each x in v, we must have this following things satisfied. We must have the strain, which is also a function of position. It's a tensor valued function, which is a function of position, should be equal to this is the strain displacement relation. The equilibrium equation following from the balance of linear momentum is this, and then the stresses and strains must be related by a fourth order elasticity tensor C if it's a stress strain relation, or with a fourth order compliance tensor if it's a strain stress relation. So these together give us so there's one more which follows from balance of angular momentum, which is this, provided there are no body couples or there are no uh, surface coupled surface tractions applied on the body. Those are the problems that we keep out of the scope of this course. So we don't have body couples, and when we don't have body couples, the stress tensor is symmetric, which means there are 6 components of stresses that we need to determine, 6 components of strain that we need to determine. Remember, the strain tensor is also a second order tensor which is symmetric. So there are 6 independent components. So 6 plus 6, 12, and then there are 3 displacements that we need to determine, which means that there are 15 variables altogether for a general problem in 3D elasticity that we need to solve for. And to solve for that, we have 6 strain displacement relations, 3 equations of equilibrium, and then 6 constitutive equations. These two are equivalent. So S is the inverse of C. So either of these can be used. So 6 constitutive equation, that makes 15 equations in total, which can be used to solve for the 15 variables that uh, that form the solution of linear elasticity problem in small deformations. Now, as far as the boundaries are concerned, on the part delta Vt, we have tractions specified. So at a point right next to where the tractions are specified, we must have the Cauchy relation fulfilled. So T bar there must be equal to sigma uh, transpose n. So this is also equal to sigma times n because sigma is symmetric, and this is the condition on delta Vt. Remember, T bar can also be 0. It can be a traction free surface, and on delta Vu we have the displacements equal to some specified quantity u bar, and again remember u bar can be a zero vector as well. For example, some of the u's would be 0 here, some of the u's would be 0 here and here as well. So these are the boundary conditions that are generally specified, and we must have that delta Vt and delta Vu together should make up the whole of the boundary delta V, and delta Vt intersection delta Vu must be equal to the null set. So this means that at no point on the boundary can you specify both tractions and displacements. That would be an overspecification. Whereas this implies that at all points on the boundary, either one of them must be specified. You cannot have a point on the boundary where none of them are specified. So none of them one of them has to be specified, and at no point can both of them be specified. That's the meaning of these two statements. So this forms the complete complexion of uh, of of a problem in linear elasticity. We will deal with basically isotropic elasticity most of the time, in which case this fourth order tensorCijkl takes the particularly uh, useful form, which is given by this for an isotropic linear elastic solid. And as we know, the lambda mu are the only two constants that need to be determined experimentally, and they can be determined in terms of a host of other constants, the Young's modulus, the Poisson's ratio, the bulk modulus being some of them. So any two of these five quantities need to be defined, and the other three can be expressed in terms of the other two. And there's a table that gives you all these different conversions between the elastic constants for an isotropic solid. Now 15 equations for 15 unknowns is a bit of a handful. So what we can do is try to reduce the number of equations by using symmetries of the problem. So this is something that you should always do. As an engineer, you should always look at a problem and try to see if it can be reduced down to a lesser number of equations, a lesser number of variables. However, there are two or three standard ways and several non-standard ones, which we are not going to discuss, but there are two or three very standard ways, standard arguments that can be used to uh, reduce a three-dimensional problem in elasticity to a two-dimensional one. So that is what we are going to see now, how to reduce this. And when you reduce this to a two-dimensional problem, what are the changes in these equations? What are the simplifications in these equations that we need to carry out? That's what we are going to learn in the next few lectures. But before that, we have to learn about the Navier's equation. Let me stop here, and we'll learn about the Navier's equation in the next lecture.